Okay. Hey, everybody. My name is Irina. I'll be talking about JavaScript and cellular automata and some genetic algorithms today. Hello. How's everybody? Yay. Awesome. I am coming from London, and I'm like 6 or 7 hours behind. So I'm very jet-lagged. So there's no reason why you shouldn't be like energized and stuff, because I'm the one that's lacking on sleep. OK, cool. So hey, I'm Irina. I am a dev team lead at Small Media Foundation. I work in London. The accent is semi-Canadian. I used to live in Vancouver. And today we'll be talking about, like I said before, about automata. Cool. Awesome. So that's a pretty confusing statement for me. What is cellular automata, first of all? Why did you want to evolve automata? What does that have to do all with JavaScript? So a little bit confusing. So I like to start with a bit of a story that is not about John Travolta. And the story is about the book that I picked up randomly at a library book sale for like $2 Canadian, which is like 5 American cents, called Complexity, A Guided Tour by Melanie Mitchell. She's written a book basically about complexity, but one of the parts of the book was about automata. And so complexity in general was like an interesting topic for me, but what struck with me was that little tiny chapter on what automata is. But before we get into that, let's talk about let's talk about how I built out what exactly automata was. So I read about it. It was kind of cool, kind of interesting. And so I got coding, and I built it out, one of the things that she was talking about. And it seemed really interesting for me. And I thought, OK, well, I know what this is all about. Maybe I can build something else with it. Cool. So that was pretty cool. I like enjoy the process. So I want to talk about the process a little bit. OK. Let's talk about cellular automata. So Melanie Mitchell, in one of her papers on computational theory and cellular automata, describes it as decentralized spatially extended systems consisting of large numbers of simple identical components with local connectivity, which is also kind of a mouthful. But if you think about it, large numbers, OK, so we're dealing with a bit of large numbers, not quite big data, but large numbers. Simple identical components, so we're talking about something that's easily reproducible or easily put together, and local connectivity, so some sort of awareness. Kind of neat, we can kind of understand, and spatially extended systems, also kind of cool, probably talking about some sort of space and time, not like the space and time continuum. So kind of understanding, but so this seems like large numbers, simple components, local connectivity, and spatially extended systems to me seems like a pretty complex subject. So before we kind of get into a little bit more on automata, I want to talk about complex systems. So complex system for me is, I wanted to like get in and Google a bunch of stuff. So I Googled a bunch of stuff. And the internet came out with the definition that it's a state of being intricate or complicated, which is not very useful. And then I Googled some more, and Wikipedia actually had a really, really understandable or relatable answer. So complexity is generally used to characterize something with many parts, where those parts interact with the other in multiple ways. So OK, this kind of ties back to the definition that Dr. Mitchell put together, culminating in higher order of emergence greater than the sum of its parts. And let's talk about that sum of its parts as we kind of go on. So keep this definition in mind, or keep this kind of thought in mind as we go through the presentation or go through this talk. Cool. So automata in general, the concept was put together initially by John von Neumann, who you might know from the Manhattan Project, or a bunch of other stuff that he was interested in. And he's basically set up an automata that is either two of the kinds. So one is, he believed one could be an artificial, which is like your central computer nowadays, or a natural automata, and you can kind of look into both. And why these two were interesting to him is that given these kinds of automata, if we are able to build out a more complex system, if we know how to build out an artificial one, we might be able to know a natural one, or if we know a natural system, we're able to build out a more artificial system. So it kind of goes to this more or less of a statement. If we understand a complex system in nature, we're able to design an artificial complex system, which is why this was so interesting for me, because you're able to kind of look into these very simple concepts and get better at either A, programming, or kind of look into actually designing something that's very simple but yet complex. Cool. So let's look at it in a little bit of more detail. So I've kind of put together three more or less things that are always true about an automata, based basically from the paper that von Neumann put together called Theory of Self-Reproducing Automata. So one is that the result is dependent on how elementary parts are defined. Two is that it has the awareness of its own parts. And three is that the operations the automata does is not directed at themselves. And an interesting way to actually think about it is that even though automata was built and thought of after the Turing machine is also in a way kind of similar. And what happens is that given those three conditions, we're able to produce a much more complicated object. So if we look at the Turing machine, we have an automaton that produces an action. It is aware of the tape that it punches through. It produces an action on something else, on the product, so not of itself. And it produces a much more different construct, a much more complicated construct than itself. So Turing machine could be kind of tied together to that entire three list of concepts. So let's go back to trait number 2, which was awareness. So how in an automata, how does awareness even work out together? So von Neumann put together his first automata with like light bulbs and wires and things like that. And I basically made a replica of von Neumann's automata, which is, I think, very likable and very understandable in exactly how he meant it to be. So basically what happens is that it's you, and you are aware of all your neighbors around you. And the entire concept of automata is basically tied about the concept of your neighbors. So it's you, and you need to know what you are up to and what your neighbors are up to. And so you are the center of attention, and everybody else is kind of around you. And once you know what they are doing, you're going to be able to figure out what it is that you have to do. So this was kind of the initial one. And so the next one that people are mostly aware of is Conway's game of life. And what this one was is that you have two states. With the light bulbs that von Neumann put together, you also had two states. One is the light bulb is on, the other one's the light bulb is off. With Conway's game of life, he obviously programmed it on an actual computer. So you would have the two states, binary, on, off. And it's kind of the same concept. It's you, and you have to be aware of your kind of neighborhood or the parts that are around you, which is neat. And then what happened is that you kind of have this space or your life, and you are able to extend as you go. So you're on a two-dimensional space. And as a cell, you're able to kind of produce based on your neighbors around you, or kind of change as your neighbors change. So there's a bunch of different initial states that you can start off with, and then as you kind of repeat your code, you're able to get to other states. So this would be kind of initial state that has worked over time. Glider is one of the famous ones that they've put together. There's another one that's a blaster that kind of looks like spaceships fighting each other, which is kind of cool. But then again, you're kind of working on this platform of life, and then you produce different cells based on your neighbors. Cool. So this was two-dimensional, so you're working on this space, and then you're changing as your neighbors change. Two-dimensional, and then you have the two states on or off. Cool. But what was interesting to me, and what I initially started off with, was the elementary cellular automata and Wolfram's take on it. So Wolfram is also the person behind Wolfram's Alpha, if you're aware of that. But he's also put a lot of work on cellular automata. And that's going to be kind of the remainder of this talk is kind of on his initial concepts and how we look into those. So it's one-dimensional and binary, which means you're still not stuck, but you still have the two states, so you're with either on or off. But instead of caring about everybody around you, you only have you, and you care about the two neighbors behind you, so you only kind of have to keep track of 3 cells at a time. And basically, your generation or your your time or your neighbors are only in one row, so it's one lattice or one array of your neighborhood or like your block. So you only kind of worry about it at a time, and then you procedurally go on. So you start off with the one lattice, and as time proceeds, you act upon your neighbors, and you produce the second lattice, and the third lattice, and the fourth lattice as the time goes on. So that's kind of like how life would proceed, basically, in this one-dimensional universe. Cool. So lattices produce over time, on and on until the generation is done. Cool. So we can take a look at that. The initial thing I've put together is a little bit visual, so it's nice. And it starts off like this. So visually, you would be able to see kind of how cells change over time, over a specific period of time. Not very good at CSS, apparently, so there's like spacing. So you would have, this is following rule 110 that he's put together. It's just like a basic hack that I wanted to see to be able to figure out how it is that the automata actually worked. But what you're able to see is kind of like these patterns that emerge, which is really interesting. But if you go back to the fact that I said that it's only you and you caring about the two neighbors next to you, this is kind of really, really impressive. So you're coming up with these patterns that just are there. And if you think about it, like you see these patterns, and I'm going to refresh the page. These patterns kind of happen, and this is based on a random initial state. These patterns are the same regardless of the initial state. So you still have kind of these triangles going down, which is cool. Which is really cool, actually. So you end up having these simple components with local information, which is my state and my neighbor's state, and the fact that they communicate kind of between one another, or they know that the state of their neighbors, we kind of create this rise of coordinated global information processing, which is a fancy way to say it's a pretty cool thing to do. You have these patterns that come up. So people have done a bunch of research on the patterns, and as you can see, a bunch of them do dominate. And they do share like this spatial structure that goes on and on and on, and especially in Rule 110, there's obviously more of them. And then what was interesting to a lot of people is the fact that the system is able to organize itself into patterns. Cool. And then because of these particular patterns and because they occur every time you kind of start on this random initial state, we're kind of back to this idea that it is a pretty complex system based on very simple rules. Cool. So again, like, let's go back to that entire thing that, okay, once we figure out kind of complex system in nature, or once we figure out being able to design an artificial complex system in nature, we're kind of able to figure out the other, or kind of have a better idea of what the other is. So it's kind of interesting. Cool. So I went on and I put together, I started putting together a library called Olivov. And what I wanted to figure out is that, okay, given like all these automata, I want to be able to start and be able to do this a little bit more dynamically and maybe change the rules or maybe change the neighborhoods and things like that. So let's talk a little bit more about this and being able to change the rules dynamically. Okay, so because you're only dealing with ones and zeros, you only have 8 neighborhoods you're ever going to deal with. They're all color-coded for your convenience and delight. So 2 states, only 8 neighborhoods, because there's 2 of them and there's 3 cells, so 2 to the power 3, 8. Cool, 8 neighborhoods you're going to be dealing with. Wolfram said, because we were dealing in 8-bit binary, there's only 256 different rules that you can follow. So that means because there was 2 to the power of 3 of different neighborhoods, we have 2 states that a thing could be, or a cell could be. We have 256 different rules that a cell could follow. So there's that many of them, and I wanted to be able to take, obviously, all of them into an account when building this out initially, and then kind of go on with this a little bit more. So given those, what happens is that you're basically given a particular rule. You are converting that rule into an 8-bit binary. which looks like this. So 110 is 0, 1, 1, 0, 1, 1, 1, 0. And it gets, those get coordinated with the 8 neighborhoods you have. And that's kind of how Wolfram set it out to be, which is kind of neat because that means that a neighborhood will always, the first neighborhood is always going to be the first number of the 8-bit binary. So you're able to kind of build that out, build that relationship out, and then do other things with it, which is neat. So then I wanted to 8-bit binary was a bit of a pain in the arse, and so you had to, that's the thing I would had to do to get it into the 8-bit stage with JavaScript, which is neat. But I got it into the 8-bit stage. But basically what I'm able to do is then I'm able to figure out, given a particular neighborhood that my certain cell is in, I'm able to assign it a rule that it should follow and it should update its state on the next life. And so given a particular, so if we look at the first lattice or the first array, given that my neighborhood is 1, 1, 1, 1, the second cell in the second lattice, given a particular rule, would change based on that particular neighborhood. So I'm able to match those up. And basically what that looks like in your terminal is when you're kind of debugging this out is a bunch of 1s and 0s. So you start learning what 1s and 0s mean after a while, which is neat also. So you're kind of in this lattice, you're changing these out and you're able to match them up. So then you're able to figure out what other rules you can apply to that or what other statements you could apply to that, which is cool. Okay, so going back, again, assigning a particular rule to a particular neighborhood can give you a bunch of different things. And what's interesting about it is that if we talk about genetic algorithms, then, and the way I've set up Olive to work right now is that, well, let's talk a little bit more about genetic algorithms. So with Cellular Automata, there's a bunch of different things that are, some of them are a little bit more simple, the other ones are less complicated. I kind of was interested in the density classification. So what that looks like is you're trying to see if an automata can vote your other neighbors out. So if we look at that particular lattice, given a random initial state, in the first ever generation, I have more black cells than I have white cells. I want to be able to have, at the end of the generation, more white cells. And given these particular rules, I want to be able to see which rules perform better. And if those rules perform better, I want to be able to keep those rules and apply them again and again and again over certain numbers of generations, whether it's 30, 40, 50, 200. Which is cool. So basically, everything is a fitness test, which is actually sounds less scary than genetic algorithm in general. So what happens with Olive is right now, as I'm kind of prototyping and working these stuff out, I'm saving history of a given generation in just an array. So it turns out to be an array of arrays or arrays of lattices. And then I'm able to perform, so I'm able to kind of grab the rest of the array and perform all the switching of neighborhoods as time passes on, and then I keep it in that particular automaton. So then I have the history of what this particular generation was like. So performing a fitness test on a history of array of lattices is actually not a big deal. So it's not that scary as a genetic algorithm sounds like. So then given the particular threshold that I might have, I could say that, okay, I want 80% of the time for this to be black, and that's a good fitness test. I'm able to kind of work through it, which is neat. So keeping history for now, really neat, and kind of works out for me. And so if, as a side note, I guess, the fact that I keep these in arrays of arrays, I'm able to see, I guess, this is what a state left and right looks like. So that's my neighborhood. And then history would have multiple of these, which is good. So structure is kind of super helpful and then makes it doable and straightforward to follow. So what's next? So I've got this kind of density classification going. It's just working through a bunch of different cells. It's just working with cells, and it's not getting me anywhere. Or it's getting me places, but I want to be able to explore more. So what I want to build out next as part of kind of this process is work with things like images or work with things like sound, because basically, you can sort of force anything to go into binary state, and then being able to explore how that binary will change over time, given a particular lattice. What I would like you to do next, or I guess what you could take away from this, it would be awesome if you explore this as well. I think it's like a super interesting topic to look into. If you're interested in this, come talk to me. I like to see what people either have done with this before or are doing with this. I always had some neat ones. A bunch of resources on my slides, and thank you very much. I'll tweet the slides out on my Twitter. They're online. Thank you.